So in this video, we're going to look at some examples of resolving indefinite integrals that have radicals in the integrand. So the first example is going to be the first of two. It says integrate 2x cubed plus 1 over 3 times the square root of x. So we have a radical down here involved in the denominator of the integrand, the function that's being integrated. So step one, as usual, rewrite the integral in your own handwriting. So we get 2x cubed plus 1 all over 3 times the square root of x. And this is dx. So we're needing to find an antiderivative of this function right here. So what we can do next is actually take and separate the function into two functions. Because I have a single term in the denominator, we can rewrite the numerator terms over the denominator terms. So I can rewrite this as 2x cubed over 3 times the square root of x plus the other function in the numerator is a 1, and I can write 1 over the common denominator of 3 times the square root of x. So we just take advantage of using a common denominator to break it up into two fractions. So it needs to be the first term over the entire fraction plus the second term over the entire, over the entire denominator, I should have said. Then what we want to recognize is that we have a constant multiple 2/3 times a function, and that function has an x cubed in the numerator. And in the denominator, the square root of x is the same as x to the 1/2 power. So I want to write it with the rational number exponent. And this is plus, from here, I have a constant multiple of another function. It's plus 1/3 times 1 over the square root of x. But the square root of x is the same as x to the 1/2. And this is dx. And now I can do a little bit of simplifying. So I have the integral. And then I have my constant multiple 2/3 times. I have x cubed over x to the 1/2. So because the bases are the same, I really get x to the 3rd minus a half. When we simplify it, we subtract the denominator exponent from the numerator exponent. So we're going to get x times 3 minus 1/2. But 3 is really 6/2 minus a half is 5/2. Plus we have 1/3, and then here what we want to do is get the base into the numerator position. So we'll do that by rewriting the exponent as a negative 1/2 instead of a positive 1/2. Once I do that, what I want to recognize is that I have the integral of a sum of two functions, which means I can break it into the individual integrals. So I get 2/3 x to the 5/2 dx plus the integral of 1/3 x to the negative 1/2 dx. And then I have a constant multiple of a function, so the constant multiple can be factored out in front of the integration symbol. So 2/3 x to the 5/2 dx plus I have a constant multiple of x to the negative 1/2, so I'm going to factor the constant multiple 1/3 out in front of the integral sign. And it'll be x to the negative 1/2 inside the integration symbol. And at this step, you're really ready to do the integration. So we're going to get 2/3 times, I need to integrate x to the 5/2. Here's the guy that needs to be integrated. We need an antiderivative of this. So this, if we were differentiating this, what we need to think about is the fact that we would use the power rule and we would decrease the exponent by 1. But integration works backwards. So instead of decreasing the exponent by 1, you're going to increase that exponent by 1. So to add 1 to it, we're really adding 2/2. So we're going to get x to the 7/2 sitting there. But your check on work is you need to differentiate this and make sure you get x to the 5/2 back. But if you were to differentiate this, what you want to notice is that the 7/2 would come down. You would decrease the exponent by 1, which would give you the 5/2 back. But you wouldn't have the original. The original is a 1 x to the 5/2. So you would need to multiply the 7/2 by 2 7s. And that's the key idea, is to recognize that when you're working backwards, you're going to need to multiply by the reciprocal of the exponent, so that when you differentiate, when the exponent comes down, you're multiplying it by its reciprocal, and the product of reciprocals is always 1. So if I'm working backwards here, it's going to be 2/3 because that's the constant multiple. My guess is going to be x. I'm going to work backwards from the power rule, so I increase my exponent by 1, but I multiply by the reciprocal of that exponent, so that when you differentiate, if you were checking your work, the 7/2 would be multiplied by the 2/7, which would give you 1, and 1 times 2/3 would give you the constant multiple 2/3 you started with. So plus, now you move to the next one, I have a constant multiple of 1/3, times, this is x to the negative 1/2. So if you were differentiating this, you would use the power rule. So if we're integrating this, we're going to work backwards from the power rule. So instead of decreasing the exponent by 1, we increase it by 1. So x to the negative 1/2 is going to become x to the positive 1/2, because negative 1/2 plus 1 is 1/2. And then we want to recognize if we were differentiating, this 1/2 would come down in front of the x, so we need to multiply by 2 to kill it. 2 is the reciprocal of 1/2. And then when you integrate, remember that both integrations give you a constant of integration, so you're really plus c sub 1 from the first integration plus a c sub 2 from the second integration. But when you add c sub 1 plus c sub 2 together, you get just a constant. So you do get two constants of integration, but we add them together into a single constant of integration. And then you look and see if you need to simplify it all. So 2/3 times 2/7 is going to be 4/21 plus 1/3 times 2, whoops, getting ahead of myself, 4/21 times x to the 7/2, don't lose the variable term, plus 1/3 times 2 is just 2/3, x to the 1/2 plus a constant of integration. And the check on work would be to differentiate this, and we would want to make sure that we got back, when we differentiated it, we would need to get back this piece right here. That's what we would need to get back if we were checking our work. So a check on work would be differentiate this and make sure we get this back, which was just the result we got from rewriting the original function a little bit differently. So we have one more example involving a radical. So this time the radical is in the numerator position. So I'm going to rewrite the original problem. We get the antiderivative of x cubed times, I have an x squared plus 1 being squared times dx. And then I can start to manipulate. I can say, hey, look, this is the square root of x to the 3rd power, but that's just the same as x to the 3/2 power if I write it as a rational exponent, times, hey, I know how to square x squared plus 1. I get x squared times x squared is x to the 4th. We get an x squared times 1 2 times, so we get plus 2x squared, plus we get 1 times 1 is just 1, and this is dx. And then we can take, now that we couldn't before, we couldn't distribute this into the parentheses before because of the squaring on the parentheses. But the moment our parentheses is to the 1st power, we can use the distributive property to say, hey, I can distribute x to the 3/2 into the x to the 4th term, plus I can distribute the x to the 3/2 into the 2 times x squared term, plus x to the 3/2 times 1 is just x to the 3/2. So we can use the distributive property to distribute those in. And then when I look at the 3 resulting terms, here, here, and here, all of them have a base x. So I can combine exponents. So this is x to the, when we multiply the same base, we add the exponents to simplify things. So it's 3/2 plus 4. But 4 is really 8/2, so we get x to the 11/2. Plus, I have a 2 times x. X will be 3/2 plus 2, but 2 is just 4/2, so 3/2 plus 4/2 is 7/2, plus, and the last one doesn't need to be simplified, so it's going to be x to the 3/2 all times dx. Again, the parentheses is necessary. And then I notice that I have the sum, the integral of a sum of 3 terms. So I can break it into the individual terms. So I get x to the 11 halves dx plus the integral of 2 times x to the 7 halves dx plus the integral of x to the 3 halves dx. And here I have a constant multiple of a function, so we can actually take and factor that constant multiple out of the integral symbol. So 2 times x to the 7 halves dx plus the integral of x to the 3 halves dx. And at this stage, we're ready to integrate. And what I want to recognize is if we were differentiating x to the 11 halves, we would use the power rule, which would involve subtracting 1 from the exponent. So because we're working backwards and integrating, we're going to add 1 to that exponent. So I'm going to get x to the 11 halves plus 1 is 13 halves. And then recognize that if you were differentiating this to check your work, here we would have x to the 13 halves. If we differentiated this, we would get 13 halves times x to the 13 halves minus 1 would be 11 halves back, but this is a 1 times x to the 11 halves. So you would need to multiply this by a 2/13. Need to multiply this by 2/13 to kill that 13 halves. So we do need to multiply this term by the reciprocal of the exponent so that when we take the product, we get a 1. And then, yeah, you do get a constant of integration coming out of that, but remember, we can add the 3 constants of integration we get when we're done into a single constant c. So I'm not going to write the individual constants. So I'm going to go plus 2 times x to the, if we were differentiating, we would subtract 1. We're working backwards, so we're going to add 1 to that exponent. So 7 halves plus 1 is 9 halves, but we need to multiply by the reciprocal of that exponent so that differentiation, the 2/9 kills the 9 halves. We do get plus a second constant of integration, but again, we just add all the constants together into a single constant at the end of the sentence. So we have 1 more to do. Again, if we were differentiating this, we would use the power rule and subtract 1. We're working backwards, so we're going to add 1. So we get 3 halves plus 1 is 5 halves. We need to multiply by the reciprocal of the exponent, and it's all plus a constant of integration. And then we do need a little cleanup right here, so I need to write 1 more line. I get 2/13 x to the 13 halves plus 2 times 2 is 4/9 x to the 9 halves plus 2/5 x to the 5 halves plus a constant of integration. If you wanted to check your work, you would differentiate this right here, and you would need to get back the integrand that you have right here on this line. You wouldn't want to have to work it all the way back to the original. What we want to recognize is all we did was make algebra steps to move from here to here to here to here. And if we did our algebra right, this expression here is the equivalent to the original. So we would differentiate and make sure we get this back.